Good afternoon, everyone. Myself, Dr. K. Ashok, Associate Professor in Physics, Marri Reddy Institute of Technology and Management. In the previous class, we discussed about how the solids are classified into different categories. Based on energy gap, solids are classified into three categories. They are conductors, semiconductors, insulators. Now our main focus is semiconductors. So basically semiconductors are based on purity, they are classified into two categories. One is intrinsic semiconductor, another one is extrinsic semiconductors. Intrinsic semiconductors are also known as I-type semiconductors. These are pure form of semiconductors. Examples are germanium and silicon. Here germanium is tetravalent. Germanium and silicon, both of them are tetravalent. Tetravalent means the valency band contains here, valency shell contains here 4 valency electrons. See here silicon, the atomic number is 14. When we observe, the electronic configuration is 1s2, 2s2, 2p6, this is second shell, and 3s2, 3p2. The outermost orbit contains 4 valency electrons. Now to attain stability like inert gas configuration, either silicon needs to leave 4 valency electrons or else gain 4 valency electrons. But it is very difficult process. That's why here with neighboring silicon atom, it will share the electrons. Sharing of electrons causes formation of a covalent bond. Here see individual silicon is sharing its 4 valency electrons with 4 neighboring atoms. So 4 covalently bonds are formed here. Next one is germanium. Germanium atomic number is 32. Here again the outermost shell contains 4 valency electrons. Same, this germanium with neighboring 4 germanium atoms, 4 covalent bonds will be formed like this. This is about the pure intrinsic semiconductor structure. But here in an intrinsic semiconductor, the main properties when we observe, intrinsic semiconductor behaves like insulator at 0 Kelvin. But at room temperature, approximately 300 Kelvin, what happened the valency electrons, means valency band electrons, can excited to conduction band. Because here the energy gap is varying 0.75 electron volts to 1.1 electron volts. So at 300 Kelvin, the electrons from valency band can excited to conduction band. The absence of electron in valency band will create a hole. So one electron appeared in conduction band, one hole is appeared in valency band. So totally the number of electrons in conduction band are exactly equal to the number of holes in valency band. The pure semiconductor conductivity is very low. That is only the drawback. And its conductivity is purely dependent on temperature. So its conductivity you cannot control from outside. We need to do some doping. So intrinsic semiconductors, whatever Fermi level if we consider, the Fermi level of the intrinsic semiconductor is exactly middle of the valency band and conduction band. So the Fermi level of an intrinsic semiconductor is exactly middle of the valency band and conduction band. This semiconductor will act as insulator at 0 Kelvin, where valency band is either partially or completely filled, whereas conduction band is empty. At above 0 Kelvin, some of the valency electrons can excite valency band to conduction band, so which causes the conductivity. Semiconductor is insulator at 0 Kelvin and conductor at room temperature. The Fermi level of the semiconductor is exactly middle of the valency band and conduction band. The major drawback of intrinsic semiconductor is the conductivity cannot be controlled from outside. Its conductivity is controlled by temperature. So, in order to alter the properties of these intrinsic semiconductors, we need to go for doping. See, what is doping? The process of adding impurities to intrinsic semiconductors. So, intrinsic semiconductors are also known as I-type semiconductor. Intrinsic semiconductor plus impurities will give you extrinsic semiconductor. Extrinsic semiconductor are also known as impurity semiconductors. So why we are adding impurities means to alter the conductivity properties of extrinsic semiconductors. If you are able to alter its electrical properties, then we can make our semiconductors which are suitable for electronic devices like diodes and transistors. The doping here, whatever doping we are doing, there are two types of impurities are available. One is trivalent impurities, other one is pentavalent impurities. Trivalent impurities means here we have three valency electrons. Three valency electrons. Pentavalent impurities means 5 valency electrons. 5 valency electrons. See, our intrinsic semiconductors are tetravalent. Suppose if you consider here, you can observe aluminum is trivalent impurity. What is the meaning of trivalent impurity? Here the aluminum has 3 valency electrons. See, this is one valency electron, another valency electron, another valency electron. These 3 valency electrons form a covalent bond with neighboring silicon atoms, whereas other covalent bond is incomplete. This absence of electron in this area causes the creation of the hole. So whenever we are adding trivalent impurities to intrinsic semiconductor, that will give you a holes are majority charge carriers. Holes charge is what you know? Positive. So these type of semiconductors are called positive type semiconductors. Positive type semiconductors, or in short form we can say it as p-type semiconductor. So whenever we are giving trivalent impurities to intrinsic semiconductor, then holes are majority charge carriers, electrons are minority charge carriers. Next, when see here, these are the majority charge carriers. Majority charge carriers, when we are adding trivalent impurity, holes are the majority charge carriers. Minority charge carriers are electrons. When you observe like Fermi level and acceptor level. Here acceptor level means this is the level of aluminum. And whatever this valency band and conduction band, these are belongs to silicon atom. So here Fermi level and acceptor level are nearer the valency band in p-type semiconductor. Next, when we consider pentavalent impurity, pentavalent impurity is nothing but phosphorus. In the name only, pentavalent means how many valency electrons are there? 5 valency electrons are there. Silicon is tetravalent. tetravalent. What is the meaning of tetravalent? Here it has 4 valency electrons. So these 4 electrons of phosphorus will form 4 covalent bonds. 1, 2, 3, 4. These 4 covalent bonds are formed. But how many electrons are there here? 5. So that 1 extra electron is available. 1 extra electron is available here. So whenever we do pentavalent impurities to n-type semiconductor, then majority charge carriers are electrons and minority charge carriers are holes. When we observe conduction band and valency band, that is energy level diagram, here donor level is belongs to, in our case, phosphorus. So phosphorus, arsenic, these all are there, but presently I am taking phosphorus. Phosphorus has how many valency electrons? 5 valency electrons. That's why this is called donor level. This conduction band and valency band, they are purely belongs to silicon. See here, Fermi level and donor level are nearer to the conduction band. So in this manner, by doping different types of impurities, we can either increase the holes by adding trivalent impurity, we can increase the electrons by adding pentavalent impurities. Before doping, intrinsic semiconductors have number of electrons are equals to number of holes. But now we changed. Because of this concentration changing, what happened, we can alter the conductive properties. So the beauty of extrinsic semiconductors is the conductivity can be controlled through concentration of doping, whereas in an intrinsic semiconductor, the conductivity is controlled by temperature. That is nothing but thermal energy controls the conductivity. When you observe combinedly, when trivalent impurity is added and when we add pentavalent impurity. So here simple in equation form, if we want to write simply I-type semiconductor plus trivalent impurity will gives rise to p-type semiconductor. In the name only itself is there, holes are the majority charge carriers. In the similar manner, I-type semiconductor, if you I-type means here intrinsic semiconductor, I-type semiconductor doped with pentavalent will give you N-type semiconductor. Here N stands for negative. Negatively charged particles are electrons. That's why in N-type semiconductor, majority charge carriers are electrons, minority charge carriers are holes. Usually, we will represent electron with filled circle and holes we will represent with undarkened circle. So this is about this thing here. In this, whatever pentavalent, we are calling it as donor impurity. Why we are calling donor impurity? Actually, required number of electrons are only 4 because 4 covalently bonded. So 1 electron is available. That's why whatever pentavalent impurity which is ready to give 1 electron. Similar manner, whenever we are adding trivalent impurities, see here 3 covalently bonds are completely filled, but 1 covalent bond is not satisfied. That's why here absence, in fraction of second this electron will move here and hole formation will be formed. This is about the extrinsic semiconductor. Next, I am going to discuss about the PN junction diode. Here, see, P-type semiconductor is formed. What is a P-type semiconductor? When I-type semiconductor is doped with trivalent impurity, then majority charge carriers are holes. Here I am representing with P positive symbol. And similarly, N-type semiconductor. How will you obtain N-type semiconductor? When intrinsic semiconductors are doped with pentavalent impurities, then majority charge carriers are electrons. Electrons are denoted by negative symbol. Here this is about the PN junction diode. Whenever, see, P type is excessive positively charged, N type is excessive negative. Whenever we are attaching each other through diffusion, the holes from P side are trying to enter into N side. The electrons from N side are trying to enter into P side. At this region, what happened, hole and electron will recombine. Positive charge and negative charge, but equal amount of charge, equal charges and opposite thing. So indirectly they gets neutralized. Equal and opposite charges gets neutralized. So this region, wherever all the charge carriers gets neutralized, this region is called depletion layer. What is the meaning of depletion layer here? The region where charge carriers gets neutralized, that region is called depletion layer. Depletion layer is nothing but what insulating layer. Insulating layer. Depletion layer is nothing but insulating layer. Now the holes from P side cannot enter into N side. The electrons cannot enter into P side. Why? Because of the barrier potential. Here this barrier potential, whenever you consider germanium, that value is 0.3 volts. What it means germanium means? Germanium doped with trivalent and obtained p-type semiconductor. Silicon doped with pentavalent and obtained n-type semiconductor. At that situation, in that p-n junction diode, the barrier potential is 0.3 volts. And if you consider silicon, same, the barrier potential is 7 volts. Until you supply this voltage for germanium, this voltage for silicon, in case of silicon, these holes from P side cannot enter into N side and electron cannot enter into P side. What it means? This diode is electrically neutral. Now to make to move electrons from one side to other side, you need to give some biasing. See, this is the symbol of PN junction diode. See here, this is the P type and this is the N type. So N type means the straight line, this triangle is P type. This is the circuit symbol of the PN junction diode. What PN junction diode does? PN junction diode will control the flow of the current in the electric circuit. See, the barrier potential just now only I discussed 0.3 in case of germanium and 0.7 volts in case of silicon. Now next, biasing. So why we want to supply biasing? Just now only we discussed here. The barrier potential is 0.3 volts for germanium based PN junction diode and 0.7 volts for silicon based diode. So if you want to move electrons, suppose this is the PN junction diode. So this is the P-type semiconductor and this is the N-type semiconductor. Here majority charge carriers are holes. Here majority charge carriers are electrons. Now if you consider this PN junction diode is based on germanium, so compulsory you need to apply 0.3 volts to move hole from here to here and electron from here to here. If you want to supply external voltage, compulsory you need to connect this P side and N side in two ways. That is called, this connection of P type and N type to the battery is nothing but biasing. Here the biasing is either forward bias or else reverse bias. So here What is the meaning of forward bias? When p type semiconductor is connected to positive terminal of the battery and N side is connected to negative terminal of the battery, then the diode is said to be forward bias. So forward bias means P side is connected to positive terminal of the battery and N side is connected to negative terminal of the battery. When P side is connected to positive terminal of the battery, this is positive and whole charge is also positive. Positive always repel. Similarly, N type is negative and these are electrons. In N type semiconductor, majority charge carriers are electrons, they are negative. Negative terminal of the battery and electrons both will get repelled. So because of this repelling between hole and positive terminal of the battery, electron and negative terminal of the battery causes movement of charge carriers towards the junction. When the charge carriers are moving towards the junction, the width of the depletion layer decreases. So the width of the depletion layer decreases. That's why we call it as this is a forward bias, is a low resistance connection. Next one is reverse bias. In the name only it is a reverse bias. P side, that is positively charged type semiconductor, that is holes are the majority charge carriers. Positively charged type semiconductor is connected to negatively charged, like negative of the battery, negative terminal of the battery. Similarly, here N type is connected to positive terminal of the battery. Negative type semiconductor is connecting positive terminal. That is indirectly we are doing reverse biasing. That's why we call it as reverse bias. See, positively charged terminal is attracted by the electrons. So electrons will move in this direction. Electrons will move away from the junction. Similarly, negative terminal of the battery is attracted by the holes. That's why holes are moving towards the junction. As the charge carriers are moving away from the junction, the width of the depletion layer automatically increases. That's why this is called high resistance connection. In the forward bias, microamperes of current will flow, milliamperes of current will flow. In reverse bias, microamperes of current will flow. Why microamperes of current flow? In the reverse bias, see, this positive terminal attracts the electrons, but this positive terminal repels the minority charge carriers, they are called holes. Similarly, here the negative terminal repels the minority charge carriers, electrons. So minority charge carriers will cross the junction. That's why a small amount of the current, that is usually called leakage current, in microamperes it will flow. In the forward bias, large amount of current flows because of the majority charge carriers are crossing the junction. In the reverse bias, microamperes of current flows because of the minority charge carriers are moving through the junction. So this is about the IV characteristics of the PN junction diode. Here we are taking voltage on x-axis and current on y-axis. See, under forward bias, what happened means, this is a P-type semiconductor, this is a N-type semiconductor. In P-type semiconductor, majority charge carriers are holes. In N-type semiconductor, majority charge carriers are electrons. So, what is the meaning of forward bias? P side is connected to positive terminal and N side is connected to negative terminal of the battery. Now, when we supply no voltage, no holes or no electrons crosses the barrier. This is called potential barrier or depletion layer. This value is 0.3 volts for germanium based diode and this value is 0.7 volts in case of silicon based diode. Means when 0 volts you apply, no charge carriers are passing through the junction. But in case of silicon, up to 0.7, no charge carriers crossing the junction. Once it reaches 0.7, these charge carriers are crossing the junction. Means in the diode, the current starts flowing through the junction. This particular voltage is called threshold voltage. What is threshold voltage? The minimum voltage at which the holes from P side can cross the junction and electrons from N side can cross the junction. That is called threshold voltage. After 0.7 voltage, you increase the voltage like 0.8, 0.9 like that. Then what happened? More number of charge carriers can cross the junction. So at a very high voltage, what happened? Completely this space charge region gets vanished. So large current flows to the junction, that we can observe here. So under forward bias, as the applied voltage increases, at a particular voltage, the current starts flowing through it. That particular voltage is called threshold voltage. Above the threshold voltage also, more charge carriers can cross the junction. Next, we will discuss about the reverse bias. So, what is the meaning of reverse bias? Let it be, this is P-type semiconductor, this is N-type semiconductor. In P-type semiconductor, majority charge carriers are holes. In N-type, majority charge carriers are electrons. When P side is connected to negative terminal of the battery and N side is connected to positive terminal of the battery, then the diode is said to be reverse biased. Under reverse bias, a small current flows through the junction. This small current of order, I told you, microamperes. These microamperes are flowing because of the minority charge carriers crossing the junction. Minority charge carriers crossing the junction. Again, if you increase the reverse voltage here at a particular voltage, what happened? Here, let it be, this is made up of silicon. In between silicon and silicon, what are there? Covalent bonds are there. So this is about the 4 covalent bonds formed with neighboring silicon atom. When high reverse voltage is applied, what happened? This covalent bond breaks down. Then what happened? Here, large number of electrons are available. So these electrons will move. These electrons are move towards the N side and holes will move P side like this. Here what happened? Large current flows through the junction. The particular voltage where large current flows through the junction, that particular voltage is called breakdown voltage. Here what is breaking? Covalent bond is breaking, so that free charge carriers are available in depletion layer. This is about the reverse bias of PN junction diode. Next, we will discuss about the Zener diode. Already I showed you the PN junction diode symbol is, this is about the PN junction diode. When you observe, the Zener diode symbol is Z. Here, this letter Z represents Zener diode. It shows. What is a Zener diode? Zener diode is nothing but heavily doped PN junction diode. Usually, Zener diode is operated in reverse bias. If you operate Zener diode in forward bias, what happened? It acts as a normal PN junction diode. But under the reverse bias, it shows some particular properties. So this Zener diode is also known as breakdown diode. So Zener diode usually like at different voltages. See here, the breakdown voltage of Zener diode is like 2 to 200 voltage. How can you decide this value? Simply depending on the doping concentration. See here, the variation of current with respect to voltage is as shown in the figure. Here the whatever forward bias characteristics which is similar to the PN junction diode. When you observe reverse bias, what happened, in the reverse bias, see here, this is a again heavily doped, right? Whenever heavily doped, this is a p-type semiconductor, this is a n-type semiconductor. Whenever it is heavily doped, usually this one is operated in reverse bias. Heavily doped means at the barrier here donor atoms will be more and here acceptor atoms will be more. What happened, here intrinsic electric field is very high. Intrinsic electric field is very high. So here whenever under the reverse bias, when no voltage is applied, okay, here let it be small voltage we are applying. When you apply a small voltage, here small current flows through the junction. This small current in the order of usually microamperes flows through the junction because of the minority charge carriers are crossing the junction. As your applied voltage is increasing, this voltage is sufficient. Here you observe in the depletion layer, what happened? Silicon will be there. See, this is about silicon. Silicon is covalently bonded with neighboring silicon atoms. This covalent bond. So here whenever you apply this external voltage addition to already existing voltage, that's why that voltage is sufficient to break down this covalent bond. Then what happened? Large number of electrons are released. That's why at lower level what breakdown will occur? Zener breakdown will occur. See, if this doping concentration is low, then what happened, when doping concentration is low, let it be this is p type, this is n type. So here let it be this is you are operating in reverse bias only, but the doping concentration is very low. Then what happened? The width of the depletion layer is anyway high, and here availability of acceptor atoms or ions are low. Then here what happened, the low field is existing. Now you need to apply here high voltage. Let it be above 6 volts. Usually below 6 volts, what type of breakdown will takes place? Zener breakdown takes place. Above 6 volts, we will say it as avalanche breakdown takes place. What is this avalanche breakdown means? Whenever, again here similar fashion, here silicon is covalently bonded with neighboring silicon. So these are the different covalent bonds. In the case of Zener diode, because of the heavily doping, internal field is sufficient to break this covalent bond. But in avalanche breakdown, what happened, you are applying very high voltage. Then here whatever minority charge carrier with high speed collides, this breaks this covalent bond. Then what happened, one electron and hole pair, they are moving under high field. Then again this electron breaks another covalent bond. Like this, in fraction of seconds, millions of electrons and hole pairs are created in this. One thing you should remember, in Zener the breakdown is because of the internal electric field. So this Zener breakdown can be reversed. That's way we are using in our houses like as voltage stabilizer. When high voltage comes, what happens? The breaker will fall. Later again we will switch will be on, breaker will be on, nothing will happen. But in avalanche breakdown, because of the collisions, this breakdown takes place. Collision will give you always lots of heat. That's way whenever avalanche breakdown occurs, the diode gets permanently damaged. Whereas in Zener diode, the breakdown can be reversed. So GNR breakdown is because of the internal excess field, and avalanche breakdown is because of the collisions. So where will we use these GNR diode? GNR diode can be used as a voltage regulator, and we can use it as a voltage reference, and even this is used in shunt resistance, and even we are using voltage shifters, and even we are using in the circuits of clipping and clamping. This is where you can see one regulator in our daily life. For AC we will use. In this also we are using GNR diode as the application.